So in this second part about multicores, we're going to look at some of the bottlenecks that were introduced with multicores as well. So looking at a simplified picture of what a multicore chip may look like, we're going to look at several of these later on in following videos. You're going to see a bunch of CPUs or cores implemented. Each one of them is going to have some shared part of the memory hierarchy. So in this example, just L1 caches. And then it's going to be some shared part of the memory hierarchy, so the higher level caches. And this is something which was actually new. That's something we hadn't seen, at least what was fairly uncommon in computer architecture before. Sharing resources between threads. Because this part of the chip now, the L2 cache in this example, had to be shared between the different threads. That meant that compared with previous to multicores, where we made a single CPU, and when we were done with the CPU, the rest of the chip was allocated to caches. In this example, we were trading core area for chip area. So we already probably compromised on how much of the chip was devoted towards the cache. And then, to make it even worse, that cache capacity now has to be shared by many threads running at the same time, possibly fighting for the cache resources, possibly kicking each other's data out. So that is a shared resource that has to be taken into account. Another shared resource that has to be taken into account is the bandwidth on and off the chip. So when you make these kind of chips, there's a limit to how many pins you can put on these chips with good economics, and there is a limit to how many bits you can send across each of these pins per second. So that becomes a hard upper limit on the bandwidth. And the more cores you have sharing, doing good work in here, the more traffic they will generate, especially if these cores also have to fight for the cache capacity. So the cache capacity per thread may actually be quite small in a multicore compared to what we were used to maybe even 10 years ago. So small capacity per thread means you're often going to miss in the cache hierarchy. It means you often have to go to DRAM. And now what makes it even worse is in this picture, it's going to be 8 of you who will have to go and fetch your data from DRAM. So this easily could become a bottleneck. So we're going to look at an example. We actually have looked at this example before. It's Lattice-Boltzmann's method from physics. And what I'm showing you here is how the throughput of a system increases when you go from 1 to 2 to 3 to 4 cores. So that means that when you go to 2 cores, you actually run 2 instances of the same program on 2 different cores. And since they are done 2 different instances, there is no interaction between them. So you really expect to have a perfect scalability. So you would expect to get a factor 2 in throughput improvement here, but you only see 50% improvement. And then you see performance degradation that we jokingly refer to as super linear slowdown. You add more cores and the throughput gets worse. So the system runs, not just that each instance runs slower, but all the instances, the 4 instances running together, in this example, produces less good work than what 2 instances using just 2 cores did. And there is a very simple explanation to why that is. So what I'm showing you here on this picture, and I only want you to look at the red curve here, is how the miss ratio changes as a function of cache size for Lattice-Boltzmann, this implementation of Lattice-Boltzmann. And the chip that I used, the multicore chip I used to run the previous experiment, had an 8 megabyte cache. So the miss ratio I would see when I run a single, just use a single core of that chip, would be roughly 3.5 in miss ratio. So 3.5% of all memory accesses will miss in the entire cache hierarchy and will have to go to DRAM. However, when I run use 4 cores at the same time running the same application, they will share the cache between them into equal parts. So that means that each one of them will get 2 megabytes of cache, which means that you will see a 5% miss ratio, the likelihood that a memory instruction that each one of these 4 threads executes, the likelihood that it will miss in the memory hierarchy is now 5% instead of 3.5. And the take-home message here is that you're going to be able to perform less amount of useful work per byte moved to and from the DRAM when you have 4 threads than when you have when you have less amount of work performed when you have 4 threads, the green line here, compared with when you have 1 thread running, which is the purple line. And now, if you're running in a mode of operation where you are bandwidth limited, so it's really the bandwidth, it's that to and from the DRAM that sets the limit, not the flips and flops. That means that operating at this point is a disadvantage compared with operating at this point over here. So that's what explains the super linear slowdown. However, if you rewrite this program, and we also discussed this one in this course earlier, you can optimize it. This is just you actually change the loop order between loops in this program. You can lower the bad news when you go to for smaller cache sizes. The bad news completely goes away. The ski slope goes away here, and it's just a straight line. So now, running 4 threads compared to before, we're roughly going to see that we perform twice the amount of work per byte moved compared with before. So if we memory bound, we should roughly see a performance improvement for 4 threads of roughly a factor 2. And that's exactly what we see. So in the optimized code is the red bar, and it's roughly twice as high, actually maybe even slightly better than that, compared with the blue bar here, which is the bar we looked at before. So you can do things. You can rewrite a code that puts less memory pressure, and that's what we have done in this course as well, with several examples of optimizing for cache. So bandwidth is a problem. So what will happen in the future? Well, it's always easier to predict the past than it is to predict the future. But we had a student here in Uppsala that tried to answer that question, and he said that, I think that the number of cores people will put on a chip is roughly proportional to the number of transistors you will put on a chip. So that's an assumption he made. And given that assumption, he also looked at what the bandwidth, and then he looked in a report that's published every year, which tells what the industry, the chip industry, what they think is going to happen in the future. How small we will be able to make the transistors, how many we'll be able to put on a die. They also say how many pins will you be able to put on a chip, as well as how fast will you be able to transfer ones and zeros and combination thereof across one of those pins. And he sat down and he tried to predict, given that I think that the compute power will increase by proportional to the number of transistors times the frequency that we plan to run those transistors with in the future, compared with how many pins you will be able to put on a chip, multiplied by the bandwidth that you will be able to carry on each one of those pins. And then he tried to predict how much compute power it was going to increase. So the balance between compute power and how much data you can send on and off the chip. And he found out that there's a tendency that the compute power is going to increase faster than the bandwidth that you will see, the bandwidth transferring data to and from DRAM. So he predicted that this bottleneck may become worse over time. Of course, the development in the world is not going to be a predicted straight line like this or a curve. It's going to be more bumps. Suddenly you have a new DDR3 technology coming in, and that's going to be a big jump here. But over a long trend, that's what he predicted, and other people have predicted similar kind of trends as well. So this is the picture of 2007. There were a couple of articles here. I think I mentioned them before. I like this one. Up against the memory wall. Never mind the cores, just hand over the cache. So it's a view that some of the high-performance computing publications in the world. It is an online publication. You can probably look up that article as well. Answering a question here about multicores. So multicore has the following bottlenecks shared between cores: memory bandwidth, register files, cache capacity, or CPU frequency. And there may be multiple correct answers here. So it's the shared thing is the memory bandwidth and the cache capacity, and of course the cores don't share register files with each other. Not even multi-threaded implementations of course share register files like SNTs, and CPU frequency is not shared as a bottleneck way between the different cores.